Let's take a look at these two partial sum sequences. Now, this first example of a partial sum sequence is what we would call a geometric sequence. You've got a starting number, and everything that you're adding is a multiple of the thing that came before it. So it looks like the pattern is from step to step, we're multiplying by a third, by another third, and we keep doing this. And of course, we can see this here because the last step is, once we get there, is taking the initial number, which happens to be 1, and multiplying it by n copies of a third once we've done that in steps. So to find this closed form, what we're going to need to do is be able to modify this partial sum sequence in order to get some canceling. We don't see any canceling immediately here. However, we can get that if we modify the original sequence by multiplying it by, well, whatever it is we're multiplying each step, that 1/3. If I multiply that an by a third, then notice that that 1 becomes a third, that third becomes a ninth, that ninth becomes a 27th, and eventually we get here to a third times 1/3 to the n. Or actually, that might be easier, more easily seen to be, we have an extra third, so 1 times 1/3 to the n plus 1. Let's get this over a bit here. All right. So what we want to do now is take these two sequences, and we're going to want to subtract them. And by doing that, I see that I have the original an minus this 1/3 an. And when I do this process of subtracting these two different partial sums, I notice that by multiplying by a third, that's what I'm doing each step here, and by multiplying everything by a third and subtracting, I'm going to get most of this stuff to cancel. This 1/3 will cancel with this 1/3, this 1/9 cancels with this 1/9. The next thing here would be a 27th, which would cancel with this, and everything on top is going to get canceled because the thing that came before this would be 1 times 1/3 to the n. So that gets canceled here. All that remains is this initial number 1 minus all that remains is this 1 times 1/3 to the n plus 1. Combine this stuff over here on the left, I see I have 2/3. 1 minus a third is 2/3 an. On the right, I guess I could simplify this down a little bit into 1 minus 1/3 to the n plus 1. And then I'm going to solve for the an and finally get my answer here to be multiplied by 3/2 on both sides. 3/2 minus 3/2, 1/3 to the n plus 1. And there's my closed form partial sum sequence. All right, well, now that I'm here, does this thing converge, and if so, to what value? That's asking me, can I take that limit as n goes to infinity of an? Well, the only thing that matters is the n, all these constant multiples come on out, and I see here that, well, that 1/3 n plus 1, limits of this form converge if and only if the 1/3, its absolute value is less than 1. And of course it is less than 1 because, well, it's 1/3, right? But if I had something like, 3/2 on the inside here, or if I had like, 7/3, that would have diverged instead. So in this case, it converges to 0, I should say. And so since this converges to 0, all this cancels out. And I'll say something like because 1/3 is less than 1 right here, and that converges to 3/2. On the upper right, we have a different partial sum sequence. In this case, it's written in this sigma notation, and I think that's there just to kind of make it not just like super obvious what it is you're supposed to do. Well, what is it you're supposed to do? We'll just write it out. Plug in that 1. It's going to be 1 over 8 minus, now plug in a 1, that's 1 over 11. Do this again, but plug in a 2 next. 1 over 6 plus 5 is 11. Plug in a 2, that's 1 over 14. Let's do one more for good measure. Let's plug in a 3. It's going to be 1 over 9 plus 5 is 14. Plug in a 3. 1 over 9 plus 8, that's 17. And we're going to keep doing this. Running out of room, so plus dot dot dot. And the last thing we'll get is plugging in this top number here, n. So just rewrite it, but with n's. So if I do that, then just like over here, I get canceling, but I don't have to do anything like combining two different sequences. It's just the bn's itself. When I multiply it, when I add out the sigma notation, I see it happen right in front of my face. The 11ths cancel, the 14ths cancel, this 17th would cancel with the next thing here, and likewise the second to last thing here would cancel with the last thing in the dot dot dots. The only thing left for my bn is 1/8 minus 1 over 3n plus 8. And that is my closed form for bn. Well, does that converge? Just like before, I'm taking the limit as n goes to infinity of bn, and that would be just all that matters is, does the limit as n goes to infinity of 1 over 3n plus 8 converge? And gosh, it sure does. What is that going to converge to? 1 over something going to infinity goes to 0, and that tells me that 1 over 8 is my convergent value. I should probably write both of these. Because it's a finite real number, it converges in both of these examples.